Alrighty, we have pretty much officially filled out Jakal Nagal here today. Next up, I'm pleased to introduce Todd Becker, who will be talking about distributed databases, why, what, and how. So please make him welcome.
Thanks. Hi, I'm Todd. I'm a principal software engineer at Family Zone, which is a local Perth-based company in the field of cyber safety for children. And so first I'd like to thank the sponsors of DG Perth 2022. I'm grateful to be up here to speak to you today. I'm going to be talking about distributed databases. Now first, a distributed database refers to a database that just uses more than one network computer or a cluster of computers. This allows them to scale up to handle more work and more data than a single computer can do. But why talk about this? Well, the amount of data that's been collected and managed has grown immensely over the past couple of decades. The rise of the internet and the proliferation of devices in that time has driven the development of more advanced software to handle that data. But as tech professionals, we don't often need to actually use this kind of database system, and the majority of software just works well with a traditional relational database. But if we do use a distributed database, we may not truly understand how it works or what its strengths and weaknesses are and how to use it most effectively. So distributed databases, however, are a vast and complex subject, and my short talk can only barely skim the surface. My aim is to give you a little understanding of some of the concepts which may help evaluate a distributed database for solving your problem. Relational databases have been around since the mid-1970s, and this model has proven incredibly flexible and useful for solving any number of problems. And in my opinion, this tech has been a cornerstone of why software now runs much of the world. A crucial feature of these databases isn't apparent in the name, and that's ACID transactions. I won't go through the full definitions right now, but to paraphrase, these properties provide guarantees on the correctness and reliability of your data, and they prevent transactions from interfering with each other. Structured query language, or SQL, was also invented at the end of the 1970s to make good use of relational databases, and it's still very popular today. So these DBs dominated the landscape for 40 years and are still prevalent today. However, towards the turn of the century, people started to find that they were needing more and more powerful systems. They were reaching the limit of how much computing power they could throw at any particular data set, but data was still being produced at an increasing rate. So some vendors did produce large specialized computers like mainframes, but they were extremely expensive and they require that big upfront investment for your peak capacity. But some of the big companies that we know today, like Google and Amazon, were just starting to experience their rise. So they needed to find ways to scale up in a big way to cope with their new demand. They didn't want to use expensive specialized hardware. If they were going to scale, they would need to do it with the commodity hardware that was readily available. So as the saying goes, necessity is the mother of invention, and the needs of these first internet scale companies led to innovation in this area, and new systems were built that could share the load across many computers. So a wave of new databases appeared to help solve the problem. In 2006 and 2007, Google published the Big Table paper and Amazon published the Dynamo paper, and these seminal papers seeded the generation of new systems that were inspired by them. And they were pushing the boundaries of what was possible at the time. Most importantly, they were very scalable. They all had some things in common. They didn't use SQL for reading and writing data, and they didn't use the relational model at all. There were lots of different approaches to modeling the data, each originally targeted at solving a specific problem. So, for example, key value databases, graph, wide column, and document, etc. The era of the purpose-built data store had begun. Choose to suit your specific need rather than a one-size-fits-all approach. The data modeling is denormalized and flexible. Some were optimized for very write-heavy workloads. Some were optimized for read-heavy workloads. And this shift away from the relational model and from SQL led to the term NoSQL being coined to emphasize that they're not an SQL or not only SQL systems. But they had real limitations as well. They didn't support ACID transactions, generally, and they did not replace relational databases, and some of the reasons for that why I'll cover. Computer scientists were a little ahead of this need. So in 1999, Eric Brewer published the CAP principle, which became the CAP theorem, And I mention it because the CAP theorem has heavily influenced the design of many distributed data stores since that time. It says that any distributed data store can only provide two of the following three guarantees: consistency, availability, and partition tolerance. Now, consistency we're familiar with from ACID transactions. Partition tolerance and availability are concepts that only exist in distributed systems with multiple separate computers. A CP system is one that gives up availability to guarantee consistency. If you write value A, all subsequent reads will read value A. If there's a network problem, it may prevent you from reading or writing data that, if it might cause problems later. An AP system is one that gives up consistency to be available. You'll always get an answer, even if the data could be stale. And if there's a network problem, it'll accept your writes and reads, even if there's a chance for it to be lost later, or even stale. Theoretically, a CA system would give up neither, but it's generally considered infeasible. This way of thinking became the de facto way to categorize these distributed databases, because it answers the important question: if something starts to fail, can I rely on the database to stay consistent no matter what, or can I rely on the database to stay available as much as it can? Before distributed databases, people were already dealing with scale problems with the concept of partitioning, which you may have heard of. Partitioning is the name for just splitting up a data set into smaller subsets or pieces, and this is for improved performance or easier management of the data. For partitioning to work, there needs to be a way of deciding where a particular piece of data belongs, and this is usually done by taking a key from your data, and this is called the partition key. And the choice of partition key can be crucial in determining the performance of your workload. Partitioning using a time field is a good choice for data sets that continually grow over time. By partitioning with a range of time means that one partition can't grow forever. And if you need to prune off the oldest times, you can just drop the oldest partitions. But for partitioning a regular string key, imagine in this example that your keys only start with the 26 letters of the English alphabet. If you wanted to split this into three partitions, you could just simply take A to G for partition 1, H to P for partition 2, and Q to Z for partition 3. Hash partitioning is another common type, where a hash function is used, applied to the key, and the result is used to work out what partition to use. This is similar to how a hash table works, which you've probably come across. But good hash functions are excellent at spreading your keys out across any range, even if you have keys that are very similar, which might not have worked in the alphabetical example. For a distributed database, to spread the load across multiple computers, clearly you need to spread the data across these computers or nodes as well. If each node had a full copy of the data, it would limit the size of your database, somewhat defeating the purpose. So what makes sense is to divide the data up and share it across those multiple computers. This sounds like partitioning? Well, it is. There's also another name for this, sharding. They're often used interchangeably, but strictly, sharding is partitioning data across multiple computers or multiple database instances. A common sharding technique is known as consistent hashing. And this type of hash partitioning is designed to avoid an awkward scaling problem. If you take this simple approach with the formula on screen, if we want to add a new node or remove a node, the shard count in this formula changes. And what that means, though, is that most of the keys now go to a different shard number. It means your data needs to be moved from many nodes to many other nodes. Essentially, you can't scale up or down. Way back in 1997, Akamai Technologies invented consistent hashing. So what it does differently is that it instead assigns each node an equal range of that hash space, and this is visualized as being distributed around the outside of a ring, which is where the term hash ring comes from. You can imagine that each node is assigned an equal piece of the pie, and the output of the hash function is mapped onto the ring, and this maps it to a node. The major advantage that this approach has is that if a node is added or removed, then far less of the data needs to be moved between the nodes, just the overlapping sections of your ring. And this overhead is relatively low and manageable. The process of moving this data around is usually called rebalancing, and this is an important thing for a database to do if it wants to allow scaling up or down without rebuilding the database. And while data is being moved, the DB might need to reroute requests internally until the rebalance is complete. In a distributed data system, there's often several copies of the data on multiple nodes as well, to guard against losing one of them. This gives the benefit of redundancy, but plus higher availability should one of the copies become unavailable. Because this also reduces the need for ultra-expensive, reliable hardware, because failures do happen anyway, so if they're embraced and handled, this is a win for reliability and cost. Okay, we've talked a bit about how data is logically distributed, but how do the nodes actually know what's going on elsewhere in the cluster and what makes them a team? They might need to know where a piece of data belongs, who's responsible for it, who else has a copy, are the other nodes healthy, failing, shut down, has been a node added or removed? How does it learn of all this? This needs to be shared, and this can't always be configured up front and never change. So I'm going to talk about two techniques that are used for this. If you can tolerate a slight delay before all of your nodes are in sync, say less than 10 seconds, then a common approach is to use a gossip protocol. A gossip protocol is sometimes also called an epidemic protocol because it's similar to the way that epidemics spread. When a node receives a new piece of gossip, it randomly picks one or more other nodes to pass it on to, and this piece of gossip spreads until all of the nodes have it. This can happen surprisingly quickly, and large clusters can converge in seconds. Why bother with this trouble though? Can we just tell all of the other nodes directly? Or maybe our network supports a broadcast. The problem with that is that it doesn't scale very well. As the number of nodes increases, the amount of network traffic goes up exponentially until the system collapses. So a gossip protocol instead keeps the overhead on the network and each node to a pretty constant level, even for very large clusters. You just sacrifice a little time. But you might also think, why can't there just be a coordinator or a leader, and the nodes stay in sync with this leader? Absolutely, that works very well for mostly smaller clusters. And there are plenty of distributed databases out there that operate with this model. But we've introduced a weakness. What happens when the leader becomes unavailable? The system can't share any new information until that's resolved. Okay, let's make the coordinators redundant, have 3 of them. But how do they stay in perfect sync? And how do they decide on a leader? So we've come up against the problem of distributed consensus. So one way to decide on something is to have a simple vote. A simple majority is enough to decide on the outcome, but computers and networks can fail at any moment, and this can skew the voting. It's a pretty fundamental need to be sure of what has happened in your system. In 1990, Leslie Lampert first wrote a paper describing the Paxos algorithm, which is the seminal work on distributed consensus. But it turned out to be hard to implement and hard to understand, and left a lot to be solved by developers. So much later in 2013, the Raft algorithm was published. It's based on Paxos, but easier to understand and to work with, and so it's been popular since then. So consistency in a distributed system needs global agreement on changes. But how does it work if instead we chose to give up strong consistency to be available? We can't just let changes be lost, can we? So instead, practical systems are instead what's called eventually consistent. This means that the different nodes in the system asynchronously replicate data to each other and then converge on just one value for any piece of data. In the meantime, it's sometimes possible to read a value that's out of date. A new value's been written somewhere else in the system, but it's not yet visible to me, but if I wait, it will arrive. But how long is eventually? Of course, the answer is it depends. It's milliseconds or often seconds, but it could be hours when recovering from complex failures. There also needs to be a way to decide how to converge these conflicting changes into one result. The simplest approach is just last writer wins. And this is a common choice in eventually consistent systems, because you just compare the timestamps and take the latest one and discard the others. It's intuitive enough, but for it to be practical, it depends on servers having fairly synchronized clocks. Algorithms exist to detect conflicts like logical clocks or vector clocks, but they don't automatically resolve these conflicts necessarily, and so a lot of AP systems decided not to use them. The reality is often never as simple as a choice between these two opposites, and this is true of CAP. The CP versus AP trade-off is more of a spectrum, and databases exist somewhere in there. A very important real-world factor that's missing from CAP theorem is L for latency. How quick it is to read or write your data is often very important. Unfortunately, there's a fundamental trade-off between consistency, availability, and latency. A big motivation for building these database systems to begin with was scale and performance. Amazon designed Dynamo to serve its shopping cart. Google built Bigtable to serve and store web search, maps, etc. Facebook built Cassandra to power its inbox search. LinkedIn and Yahoo have similar examples. These systems needed scalability and performance, and this is a big part of why they were AP systems. The potential trade-off you make, as we discussed, is the chance of reading inconsistent data. This may be a non-issue when your data doesn't change much. These systems can be a great fit for collecting mostly immutable data like telemetry, events, messages. And they're also great for use cases where you're okay with the occasional glitch. And I'm sure that on the rare occasion an item has just mysteriously disappeared from someone's Amazon shopping cart. Has this hurt Amazon's reputation or profits? No. And not every business who made this trade-off feels the same way though. Uber is one example that I'll talk about shortly. After a while working with these databases, people were starting to realise the CAP theorem, while technically true and insightful, wasn't really nuanced enough for them. It's only an algorithmic property. It doesn't guarantee that AP systems are actually up all the time. So there are other ways to think about it. So Rick Houlihan introduced this tasty concept called the pi theorem. You can choose two of these three desirable properties of your data store: pattern flexibility, infinite scale, and efficiency. And Rick called it the iron triangle of purpose. So for some examples, a relational database is a PE system. It's very flexible to query, it's usually quite efficient, but it definitely has a scaling cap. A NoSQL database is an IE system, typically, because it scales very well, it's got great efficiency, but you can't do flexible queries that you haven't planned for to begin with. A queryable data lake might be an IP system, huge scale, low efficiency. So when you next need to choose a data store, you should consider this model as well. In addition, some people learnt the hard way that eventually consistent systems could be more trouble than they're worth. For instance, Google published this, and I'll paraphrase: it's hard to build bug-free systems when the database doesn't guarantee consistency. The DynamoDB offered by AWS has the option of strong consistency within a region. Azure's Cosmos DB has the option of strong consistency. Google's three main databases for internal and external use, they all offer some form of strong consistency. Some NoSQL data stores have since been extended or even custom built to support full ACID transactions. For example, Apple Open Source Foundation DB, which is a highly scalable NoSQL database that supports full ACID transactions. And it powers Apple's CloudKit service, and Snowflake uses it to store their metadata. Research continued in big tech, as well as academia, and a new generation of databases has emerged in the recent decade, and these have been dubbed New SQL. It's a play on NoSQL, but it represents that they're a new generation of SQL databases. They can provide much higher scalability and availability, but without giving up the advantages of a relational database. And this was seeded again by more papers released by Google, F1 and Spanner. This was novel, and it inspired the creation of a number of similar databases. Some of these are CockroachDB, TiDB, and UgiByteDB. So I mentioned a little startup you might have heard of earlier, Uber. Uber handles billions of transactions per day now on their core order tracking system. If you've ordered an Uber or an Uber Eats, it's probably been through there. And this was originally built on the Cassandra database, and they embraced Eventual-Consistency in this system in order to get the scale they needed. However, they were still frustrated by occasional consistency problems and the complexity that's added to their code. They've publicly talked about this and how they've done a full rewrite now to move to a consistent store, and they're using Google Cloud Spanner as the primary DB. As more examples, Netflix have blogged about how they're making use of CockroachDB, and we're using CockroachDB at Family Zone. This all sounds too complicated. Why should I bother with a distributed database? Well, if you don't have a need for high scalability and high availability, you probably don't need one. However, more and more apps find themselves needing to handle bigger and bigger data sets, and it's sometimes said that the common app is becoming a big data app. The distributed databases that exist today are the culmination of decades of research and development. So you can have your cake and eat it too, with scalable transactional databases that support SQL and the relational model. And there are choices available out there in addition to what's offered up by your cloud provider. Beware of giving up strong consistency, or at least be sure why you don't need it before you give it up. If you need to work around the database, then perhaps it wasn't the ideal choice for your problem. Despite these breakthroughs, there's still no one-size-fits-all distributed database solution. There are generally purpose-built data stores that might be ideal for your particular workload. Perhaps an analytical database was what you actually needed, or even a graph database. So do your research before you jump, and don't choose just based on the hype or the marketing. Thank you for listening. Do we have any time for questions? Are we out?
I think we've got time for one or two quick questions. We are on a time, but yeah, if there are questions for Todd. Sure.
Would you recommend you mix and match databases, different databases in one application?
I think there's probably a lot of nuance to that, but I think if your organization justifies it, so you have a big enough need for using more than one database, because you need people that understand the different technologies, you need to maintain those different technologies. So if you need the scale, yes. If you don't need the scale, that's where I'd consider just making do with one. But absolutely, the point was that they're purpose-built, so if one suits your need very well, use it for that need. But that's easy to say, and reality usually dictates that only if it's got the money behind it to justify it.
Okay. Thank you very much, Todd. We'll wrap it there. Please give Todd another round of applause, and we'll move to our next sessions.